At first light, the tower in northeastern Wyoming does not look like a mountain. It looks cut. The walls rise in long vertical flutes, as if grain has been pulled upward through stone. The top sits strangely level, like a surface exposed rather than built. At the base, giant broken columns lie scattered in the grass like splinters from something that should not have been able to break this way at all. From a distance, the object is familiar before it is geological. It resembles a stump, not a hill, not a peak, the end of something removed. And once that comparison enters the mind, the scale becomes difficult to explain normally. If this is only rock, why does it so often look like the remnant of a form we already know? The accepted explanation begins deep underground. Devil's Tower. Devils. And according to the National Park Service and generations of geologists before it, is an igneous body, molten rock that forced its way upward roughly 50 to 60 million years ago, cooled below the surface, fractured into immense columns as it contracted, and was then exposed by millions of years of erosion. The surrounding sedimentary layers wore away. The harder core remained. That account is not fringe, it is careful, technical, and in many respects persuasive. Similar columnar structures appear in volcanic settings elsewhere in the world. The tower's rock is identified as phonolite porphyry. The visible cliffs around its base preserve older sediments from vanished seas. In broad outline, the story is coherent. Magma rose, rock cooled, water stripped the cover. A monument appeared. And yet the official explanation carries its own hesitation. Even the agencies that present it admit that the details are not settled. Was this a stock, a laccolith, a volcanic plug, a mer-diatreme structure, or something adjacent to all of those categories? The tower is famous not only because geologists study it, but because they do not entirely agree on how exactly it formed. There is limited evidence of the kind of surface volcanism people expect when they hear the word volcano. The ash, the crater, the broad lava fields, the obvious wreckage of eruption are not plainly there. The answer offered is erosion. The same process that exposed the structure also erased the evidence needed to identify it with certainty. That may be true, but it means the official explanation is strongest at the level of type, and weakest at the level of direct reconstruction. Something happened here, the shape remains, the mechanism is still being argued. That uncertainty is where the hidden theory enters, not as a cartoonish rebellion against geology, but as a serious question about classification. What if some of the landforms we have been taught to see as purely volcanic, erosional, or tectonic are, in a small number of cases, the mineralized remnants of biological structures so old, so altered, and so large that later observers place them into the nearest available geological category? Not ordinary trees, not forests in any human sense, something from a vastly older biosphere, preserved not as wood but as stone. Most versions of this theory are overstated, some are plainly careless, but what matters is not the loudest claim. What matters is the underlying possibility that certain formations are not simply resembling stumps by coincidence, but retaining the geometry of growth beneath a later explanation. The question is not whether the idea sounds strange, the question is whether the pattern deserves more scrutiny than it has received. Begin with proportion. Devil's Tower rises about 867 feet above its base, over 1,200 feet above the river valley, and its columns can reach widths of 10 feet. Those numbers are usually cited to emphasize volcanic grandeur, but they also emphasize something else. The structure is not chaotic, it is organized. The tower does not present as a pile of broken lava. It presents as a coherent vertical bundle, a mass of long parallel units, bound tightly enough that the whole form remained standing, while the surrounding strata disappeared. Geology explains the columns as contraction cracks in cooling igneous rock, and there is real force in that explanation. But morphology matters. People respond to shape before theory. This is why the comparison returns in photograph after photograph, decade after decade. The object reads as cut wood because the eye recognizes continuity, outer wall, interior fiber, and a flattened crown. That resemblance may be misleading. Nature often repeats geometry across different processes, but once resemblance survives measurement, it stops being a joke. It becomes data of a softer kind. The stone remembers. Even when the label changes, the form stays there. Now widen the frame to New Mexico. Some shiprock stands alone from the desert floor like a dark core with thin walls extending outward for miles. Geologists call those extensions dikes, magma that forced its way through fractures and later resisted erosion better than the surrounding rock. The description is conventional and technically sound, but conventional language does not remove the visual grammar. A central mass, radiating ribs, a dominant vertical body with hardened linear structures extending into the landscape like buried supports. In one case, it is a volcanic neck and feeder system. In another interpretive vocabulary, it looks uncomfortably close to a root flare frozen in stone. The same conflict appears again and again across mesas, buttes, monoliths, and isolated towers of the American West. They are described through mechanics, yet perceived through anatomy. And in that gap, matters. When many observers across time independently reach for the same biological comparisons, the comparison itself becomes part of the record, not proof, not yet, but a pattern the official language has never quite dissolved. There is also the matter of petrification, which quietly removes one of the easiest objections. The objection is simple. Wood is wood, stone is stone, and confusing the two is childish. But the fossil record does not permit that simplicity. In Arizona's petrified forest, entire logs have become almost solid quartz. Silica carried through groundwater replaced organic tissue cell by cell as the original material decayed. The result is not wood coated in mineral, it is wood translated into rock while preserving structure. In some cases, up to the logs fracture into repeated segments so cleanly that visitors still ask the old question, who cut the wood? The park's own explanation is that quartz is brittle, and tectonic stress broke the buried trunks like glass rods during uplift. That answer is plausible, and it proves something important. Biological forms can survive burial, mineral replacement, compression, fracture, and deep time, while ending as objects that later generations mistake for something else. This does not prove that a tower is a trunk, but it destroys the lazy claim that biology cannot cross fully into geology. It can. The record shows that it already has. Old photographs deepen the unease. In the late 19th and early 20th centuries, photographers in the Pacific Northwest documented logging scenes around stumps, so wide that people built shelters inside them. Families posed in carved living rooms cut from giant cedar and redwood remains. Work crews stood on platforms above trunks thicker than houses. These were real trees in recorded history, not myth. Their size is often treated as quaint evidence of a lost wilderness, but their deeper significance is that human memory once included vertical organisms far beyond modern expectation. The industrial age did not simply erase forests, it reset the imagination downward. After that, scale itself became suspect. Once the upper range of biological form is forgotten, resemblance at larger scale is dismissed automatically. A stump can be enormous, a forest can define an economy, and an organism can become landscape long before it becomes legend. That does not mean every flat-top butte is a tree remnant. It means the mind that rejects the possibility is often using a baseline already shaped by absence. What changed was the explanation. Before that, the world may have looked less bounded than we now assume. To be fair, mainstream geology deserves its strongest case. Columnar jointing is real. It is well documented. When molten rock cools and contracts, the stress can produce polygonal fractures, often hexagonal, and those fractures can create striking vertical columns. Devil's Postpile. In California, the Giant's Causeway in Northern Ireland, and basalt formations across Iceland and elsewhere demonstrate that nature does not need biology to generate regularity. The same is true of erosional remnants. And harder material survives while softer rock is stripped away. buttes, necks, towers, and plugs can emerge without any hidden arboreal history. This is not a field of ignorance. It is a field with mechanisms. The problem is narrower. Those mechanisms explain the existence of columns. They explain resistant cores. They explain talus. What they do not always explain is why certain sites generate the same biological reading even after explanation is supplied, or why some of the most iconic examples may be geologically disputed in their exact formation pathway. The mainstream account answers most of the process. It does not answer all of the resemblance. And sometimes resemblance is how a buried process first announces itself. And the pattern becomes more unsettling when you stop looking at a single monument and start looking at a category of forms. Across the American West, there are isolated towers with fluted sides, mesas with flattened crowns, circular uplifts, organ pipe cliffs, radial dike systems, petrified forests, silicified root-like networks, and vast sedimentary exposures that appear scoured down to a harder internal structure. Most of these features probably have conventional explanations, and many certainly do, but the pattern does not disappear simply because each case can be handled separately. A repeated visual logic runs through them. Central core, outer bark-like rind, fractured vertical texture, ring terraces, radiating supports, broken segments at the base. The terms used in naming them are revealing. Tower, postpile, chimney, organ, stump, neck, plug. Language keeps circling back to anatomy and manufacture because the land itself keeps presenting those cues. Geology treats that as metaphor. The hidden theory treats it as residue. Somewhere between those positions is the possibility that morphology has been noticed, named, and then quietly neutralized by interpretation. Maps add another layer. On a topographic sheet, a strange object becomes less strange because the map is designed to abstract irregularity into contour, symbol, and legend. Yet maps also preserve relationships the eye misses on the ground. Look at the way some isolated formations sit within basin structures, ring features, and drainage lines that suggest former systems rather than solitary accidents. Look at how resistant masses sometimes remain, where the surrounding terrain appears peeled back, not built up. And look at radiating igneous dikes that can extend across miles of country from a central core. The official explanation sees feeder pathways from a magma chamber. The hidden theory asks whether some of those pathways might also resemble the internal geometry of living support systems because form is being inherited from an older template. The question is not settled by the map, but cartography has a habit of preserving patterns long before disciplines agree on what those patterns mean. Aerial perspective removes drama and sharpens design. From above, some of these formations look less like random outcrops and more like exposed cross-sections of something once integrated, then stripped down to the elements that could survive. Timing is another pressure point. Much of the accepted reconstruction depends on enormous intervals during which exposure and erasure happen together. The tower formed underground. Then over millions of years the cover vanished. The volcanic evidence may have been present, then lost. The crater may have existed, then been removed. The debris may have surrounded the site, then been carried away. All of that is geologically possible. Deep time allows for astonishing subtraction, but deep time also allows for other kinds of preservation, including asymmetrical preservation. If one explanation can appeal to erosion to account for missing evidence, another explanation can do the same. If the absence of bark, branches, leaves, or roots is enough to dismiss an arboreal interpretation, then the absence of clear volcanic architecture should at least weaken confidence in a perfectly resolved volcanic one. Absence cannot be used selectively. What remains is what remains. And what remains in these cases is often a resistant central form whose shape invites a biological analogy more strongly than the surviving context supports any single geological reconstruction. The burden, then, is not only on the strange theory, it is on every theory that depends on what is no longer there. There is also the bureaucratic problem, which is less dramatic than conspiracy and far more powerful. Scientific institutions are built on categories, departments, funding lines, and methods optimized for normal cases. A monolith enters the record as geology, and from that point forward it is surveyed, sampled, protected, litigated, and interpreted as geology. Botanists do not core it for vascular pattern because it is not classified as biological. Paleobotanists study fossil wood at hand scale, not landscape scale, because their discipline is not funded to ask whether a mountain once belonged to a larger organism. Park agencies inherit prior definitions. Mining law distinguishes mineral from timber. Academic careers advance through specialization, not through claims that cross from volcanology into deep time biology. In most cases, this conservatism is healthy. It prevents nonsense from taking over. But it also means certain questions become professionally unaskable long before they are carefully disproven. The truth, if there is one here, would not need a secret committee to hide it. It would only need inertia, paperwork, and the quiet authority of a map legend. Our photographs from the 19th century complicate the story in another way. Early landscape photography often captured terrain before highways, interpretive signs, quarry blasts, and restoration projects standardized the view. In those old images, certain formations look rawer, less explained, more anatomically suggestive. At the same time, industrial photography documented a civilization cutting through old growth on a scale modern viewers barely recognize. Enormous stumps stood across cleared land like a field of amputations. That imagery mattered. It offered a living bridge between tree form and terrain. People who had seen monumental stumps in logging country would have had a different instinctive response to flat-topped, fluted rock forms than viewers raised among second-growth timber and road cuts. Then, as geology professionalized and public education codified its categories, the interpretive bridge narrowed. One class of objects became biological relics. Another class became geologic structures. The resemblance between them survived only as a curiosity. The record is still there, not because photographs prove the giant tree hypothesis, but because they show how recently human beings still possessed an ordinary visual memory of organic forms large enough to blur into landforms. Another point is scale repetition. In ordinary science, a pattern gains credibility when it appears across multiple magnitudes. Veins repeat in leaves and rivers. Branching appears in lungs, deltas, and lightning. Fracture patterns recur in dry mud, frozen lakes, and cooling lava. The mainstream position uses this principle one way. Similar forms can emerge from different processes, so resemblance proves little. That is correct. But the principle also works in the opposite direction. When a hidden theory points to recurrence across scales, it is not automatically irrational. If giant biological structures ever existed, one would expect their remaining geometry to be misread as geology precisely because nature reuses efficient patterns. The larger the organism, the more its support systems might converge with forms we now classify as structural or tectonic. This does not establish the theory. It clarifies why the theory survives. It survives because at the level of shape, the world keeps offering analogies no one can completely dismiss. The eye sees a stump. The handbook says intrusion. The two perceptions coexist, are unresolved inside the same object. And then there is the psychological resistance created by number. 40 miles is not merely large, it is destabilizing. It exceeds the scale at which most people can picture an organism without slipping into fantasy. That is why the most extreme versions of this theory fail so quickly. They ask the mind to jump from known botany to continental mythology in a single motion. But serious investigation does not begin at the largest claim. It begins at the surviving form and works outward. If one imagined a former biosphere under different atmospheric conditions, different pressures, different chemistry, or simply over incomprehensible spans of deep time, then extreme scale becomes less a punchline than an engineering question. What support would such a form require? Then what mineral traces would replacement leave? What kind of terrain would remain after collapse, burial, and stripping? Most of those questions have not been studied because the premise is unfashionable. That does not make the premise true. It means the argument is not over evidence alone. It is over the boundary of what professionals are willing to model. The pattern does not disappear. It simply moves outside accepted categories. So the hidden theory in its strongest form is not that every mesa is a stump or that every monolith is a petrified tree. It is that a small but unsettling subset of the world's most anomalous formations may preserve the mineralized architecture of biological structures from a past no modern discipline is designed to recognize whole. The official explanation remains useful and in many cases probably correct. But usefulness is not the same thing as completion. What remains in the field are forms whose appearance, fracture, isolation, and context continue to generate questions the standard labels do not fully quiet. A tower that may be an intrusion, a neck whose dikes look like supports, quartz logs that still look cut, old stumps so large they reset the imagination, institutions that classify first and investigate within the class afterward. None of this proves a forbidden forest, but taken together, it creates a discomfort that the simple story does not remove. And that is the unsettling reframing. Perhaps these places are not mysterious because the past was magical. Perhaps they are mysterious because the present is categorical. We inherit names, maps, museum text, and disciplinary borders, then mistake them for final vision. Hardly but the stone keeps its own record. Shapes persist after causes are forgotten. A world can be reinterpreted without being understood. What changed was the explanation. The object stayed where it was, under the same weather, carrying the same impossible silhouette into each new century. Maybe Devil's Tower is exactly what geologists say it is. Maybe Shiprock is only a volcanic throat with radiating dikes. Maybe every stump-like mountain is simply rock behaving like rock. But if even one of these formations belongs to a deeper biological history than we have allowed, then we are not looking at scenery. We are looking at the amputated evidence of a vanished scale of life. And the real question is not whether the theory sounds strange, but whether anyone with the tools to verify it has seriously looked.